Alright, thanks for watching, and yes, I saved the best for last because here is, in my opinion, the neatest way of checking for uniform continuity. And it has to do with derivatives, which technically is part of chapter 5, but this is too good to wait. So, without further ado, here's the fact. So suppose f is continuous on a comma b, and f is differentiable inside. Is differentiable, meaning that f prime exists in the open interval a comma b, and moreover f prime doesn't go to infinity, so it is bounded, and f prime is bounded, meaning that there is capital N positive such that f prime of x is always less than or equal to capital N. Less than or equal to capital M for all x in a comma b. Then f is uniformly continuous on that interval. And you might be like, wait a moment. Well, AB is compact, so f should be uniformly continuous already. This is true, but here's the beautiful thing about this theorem. This actually holds for any kind of interval. So even if you did that for a comma b, or like half open intervals like a comma b, or even infinite things like a comma infinity, or even the real numbers, this theorem would still be true, provided that here you replace the interval by the interior. How cool is that? But just to make things simpler, I assumed closed interval a comma b. And here's some applications so you see how awesome this is. So first of all, consider f of x equals 1 over x on the interval 2 comma infinity, which we've seen before, but now we'll see a much faster way of doing this. Then it's continuous here, differentiable in the open interval 2 comma infinity, and moreover, if you take f prime of x, so the absolute value, that is the absolute value of 1 over x squared, and that becomes 1 over x squared. But you see, if x is in 2 comma infinity, x is greater or equal to 2, so 1 over x squared is less than or equal to 1/4. So therefore, f prime is bounded by 1/4, and in particular, it's automatically uniformly continuous. So therefore, f is uniformly continuous on 2 comma infinity. How cool! And the point is, those assumptions are usually very easy to check, so which gives us a very easy way of checking for uniform continuity. And in fact, here's another example. So what if you take sine of x? Sine of x on r. Well, again, check for the derivative. Well, f prime of x, that is cosine of x, but cosine of x is less than or equal to 1. So this is bounded, therefore f is uniformly continuous on r. On r. So you see how neat is that? The good news is the proof is equally neat. So let me discuss this now. And the proof uses a fact, hopefully you remember from calculus, called the mean value theorem. So a fact, so you the real MVT, if you'd like, all that it says is that f of b, so if you have any numbers a and b, then f of b minus f of a over b minus a equals f prime of c for some c between a and b. A and b. So in other words, picture-wise, all that this says is that the slope of the secant line is equal to the slope of the tangent line somewhere. So if you have your function like that, so this is a and b, and this is f of a and f of b. Then the slope of this line is rise over run, so f of b minus f of a over b minus a. So this slope is, again, this thing on the left-hand side. Whereas f prime of c is just the slope of the tangent line. So what this is saying is there must be some point where the slope of the tangent line equals to this slope. And in fact, notice it's somewhere here. And that's f prime of c. So you see, in other words, given that secant line, there must be some point where the tangent line is parallel to that secant line. All right, and how does that help us prove our thing? You'll see in a second. So here comes a proof. Proof of the fact. So let epsilon be given. And we know that f prime is bounded, so we know that there is capital M positive such that f prime of x is less than or equal to capital M for all x in a comma b. And in fact, you'll see in a second why, but let delta just be epsilon over M. Then if x and y are in a comma b, then, well, by the mean value theorem, we have that f of x minus f of y over x minus y equals f prime of c for some c between x and y. Okay. And of course here I assume x is not equal y, because otherwise the result is already true. And therefore, if x and y are close enough, hence, if now we have x minus y is less than delta, then, well, let's calculate f of x minus f of y. But you see, by the mean value theorem, this quantity just equals x minus y times f prime of c. So if you want f prime of c times x minus y, but that's just f prime of c times x minus y. But here's the thing, so f prime, we know it's bounded, so it's less than or equal to m times x minus y. And now, remember, x minus y is less than delta, so this is less than m times delta, which was epsilon over m, and this cancels out. So m and m cancels out, and we have victory. And therefore, f is uniformly continuous on that interval. And if you're in my class, congratulations, this was the last required thing we had to learn. And the next time we'll just do review. I'm super proud of you, just saying. All right, thank you.